I want to speak to the boron and calcium observation and potential balancing reactions. So as you may be aware, we have done, if I can share this, can you see what I'm showing here, this gray area? Can you see that?
We see.
Okay, so this is a video of a sheet of aluminium in water, and I will turn on the ultrasound at 43 kilohertz. And within a few seconds of the sound starting, we get resonant interaction and the production of what was initially called two spots. And they find their locations, and then they stay there and they work hard in those locations. So ultimately, it ends up by cracking the aluminium in specific zones. So it's a very simple experiment. It costs $35 and takes about 20 minutes to conduct and learn. Using that information, we produce these structures, which are exactly and precisely the ratio of the yin-yang. Absolutely. Anyone can do this from 5 years and up. It's been replicated widely. And when you run the experiment for a few minutes, you end up with the start of a breakdown. And you can see there's a vortex going this way around, which is the same ratio exactly as a spiral galaxy. And there's another vortex going the other way around. Okay. And when you zoom into these structures, you have accretions, and it's where the vortex comes and collides with itself. Okay, it's not quite on the center point, it's off-centered. And if we look on one side here, and I'm looking at the analysis on this side, we have as much as 35% by weight of boron in one spot on this central point, and 31% again. Now, there is 0 calcium on this side. On the other side, we have similar, the spot here, which is under here, this is the carbon tape. So I have to look at the closest to the center point, and it's off center. It's off center in a different way on the other side. But if we look at 2 spots here, we see that we have by weight 4.37% calcium, and there is 0% boron. So on one side, if you imagine this was concentrating impurities in the reactor, you would imagine that this would have boron and calcium, and this would have boron and calcium. But in fact, what you have is on this side, you have only boron and 0 calcium. And on this side, you have only calcium and 0 boron. Okay. Now, if we look at the Parkhomov reaction tables, if we take the paramagnetic oxygen molecule and the paramagnetic aluminium, and we fuse them, we get isotopes of calcium with large net energy gains. And if we go and look at the fission of aluminium to boron and oxygen, we end up with large negative megaelectron volt gains. Losses rather. So what I'm suggesting, therefore, is that on one side, the vortex is assembling matter, and on the other side, it is disassembling matter. And therefore, unless you can separate the 2 vortex ends, you will not gain excess. You'll, in fact, have excess cooling on one side and excess heating on the other side, but the actual action occurs at almost infinitesimally small point, and the nuclei is transferred from one to the other. That is my point. So when you're observing, in this case, it's easier because we only have water, hydrogen, oxygen, and we have aluminium. And so the calcium is heavier than aluminium and needs oxygen and the aluminium. And the boron needs to fission the aluminium and leads to the production of the oxygen that comes on the other side. So I'm wondering if you are considering that these processes are balancing the reaction. I've observed this exact structure with the same exact proportions in Alexander Parkhomov's 225-day reactor. I've shared that widely at my presentation in ICCF 22. I've shared the exact same structure on a Marsa gas on a tungsten rod. I've seen the exact same structure on a vibrating plate in a palladium-coated vibrating plate. It's ubiquitous. and you tend to find that the heavier elements, so if you actually look here on the side where you're getting the heavier elements formed, we're even getting some silver, okay? On the side where the lighter elements are formed, it's much less. You're getting mostly carbon, nitrogen in there. So have you considered that we're not getting energy out of these systems? Because the best example I can give is the presentation given on ICCF 20 by the late Dr. Mahadevan Srinivasan. They had a electric arc furnace at the 11 megawatt or 14 megawatt level running for 11 weeks in southern India, and it produced 3 extra tons of silicon per day and 1 extra ton of iron per day every day for 11 weeks. And there isn't a huge hole in India. So there must be some balancing going on. So for instance, hydrogen could be being synthesized by tearing matter apart, and that's highly negative. And carbon and oxygen are fusing together to form silicon, for instance, and that is highly positive. And it is through the yin-yang process, which any 5-year-old can conduct this experiment in 20 minutes, you get a balancing action. And so that is my point about you're observing both the production of a lighter element. I know in your case, you've actually starting with nickel, so that is heavier than calcium. But in that reactor, am I